Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, today we're hosting Kanishka Baduri from NASA Ames. And Kanishka has been working in the area of distributed learning and deep mining for quite some time, since his PhD at University of Maryland, Baltimore County, and after which he was a researcher at TU Dortmund for some time, and then he moved to NASA Ames, where he's been working on interesting things since then. Today he'll tell us about algorithms for outlier detection.
Thank you, Misha. So my talk today is about two separate topics. The first one is outlier detection from large databases. The second one is about model fidelity and model checking in large distributed systems. So the first part of the talk will focus on outlier detection and how you can speed that up using both an indexing technique on the database side and also some parallel programming techniques from the system side. So this is a joint work with my colleagues Brian Matthews and Chris Gianella. Brian is at NASA Ames and Chris is at MITRE Corporation. So this was the work we presented in last week's Security conference. So here is a brief roadmap of the presentation. First, I'll introduce the subject, and then I'll give a little bit of background on what the state of the art is and what we are trying to do. That will fall into the contributions part. Then some of the algorithms that we are interested in and we have developed and how they perform in the experimental results, and finally a conclusion to end the talk. So this is the setup of the problem. So we are given a data set where each row is an instance, and for the time being we're assuming that they are IID samples. Each column is one of the variables. Here I have an example of the aviation domain in which I work in. So each column can be like speed, altitude, roll angle, pitch angle of the aircraft, and many other parameters. So we have 500 or 600 parameters that is being measured at a frequency of 1 Hertz. And the idea is to apply outlier detection techniques to find rows or instances of this data set which are abnormal. And there are several ways you can define abnormal, and I'll propose and use a particular one of them. So naturally the question comes, where can these be used? We all know outlier detection can be used in many places, and here are a few examples. Anomalous user behavior in social and information networks. So you have a huge network and you want to find a user who is abnormal than the rest. So typically what you can do is you can define a feature space for each user in the high dimensional space, embed the feature in that space, and then run this typical outlier detection algorithms to find the abnormal user. This is just one way of doing it. Misconfigured machines in cloud infrastructure is another interesting example, where what you do is you take all the machines in the system and then you run a typical distributed or parallel outlier detection technique that runs on the core of each of these machines in the distributed scenario, and then you come up with a set or a collection of machines which is misconfigured or behaving abnormally compared to the rest. Fraud detection in large transaction database is a very interesting application, and much work was going on since the last 10-15 years now. Lastly, the one that we work on is abnormal aircrafts using operational data. So whenever there is a commercial airlines flying from point A to point B, there is a huge amount of data that is being collected of the order of several gigabytes. The idea is to leverage all of this data to figure out which aircraft is most abnormal with respect to the other aircrafts. That's the idea that we have, and we are working on that one problem. So here is the definition of outlier that I'm going to use. I'm going to use the distance-based outlier. The idea is very simple. So an outlier is a point which is very far from its nearest neighbor. So here is the red point, which is an outlier, and the reason being, if you look at its nearest neighbor, one of the green points, it's quite far from its nearest neighbor. So that's the idea. So the naive approach of doing outlier detection is very simple. For every point, you find its nearest neighbors, rank the points according to the distance to its nearest neighbor, and you have the entire ranking of the outlier. Here is one example. The red ones are the outliers, and the bigger means more outlier, and the green ones are the nearest neighbors, and the arrow, the line in between is how far it's from the nearest neighbor. So the farther it is from its nearest neighbor, the more outlier it is. And that's the traditional ranking in which you can find near outliers from top to bottom. As you can see, if you apply the brute force algorithm, you have to compute the entire distance matrix, which is extremely expensive for large databases. It doesn't scale at all. there are several relaxations to this problem which have been proposed in the literature. The one that I'm going to focus about will guarantee that I get the exact same outliers that is found by the brute force approach. There are approximation techniques which work on the same problem, but I'm not going to talk about them. So here is one relaxation which was proposed in 2003 in KDD and by Bay and Schaubacher. So what they said is, instead of finding all the outliers, let's just find the top T outliers, where T is a user-defined parameter. And why this is important? Because of the following reason. You can actually reduce the computational complexity by a huge margin. The way the algorithm works is, you first set a buffer to size T, and you pay a price by looking at the first T points of your database and finding its actual nearest neighbors. So here is the pictorial representation. So on the left axis, I have some points, and let's say that I know which points are the most outlier. In the true scenario, you won't know that, but for illustration, it's easier to see that. And I pick the first 3 points, let's say T equals 3, and put them in the buffer and find the true nearest neighbors of those points. And along with that, what I do is, I also find a cutoff threshold which I call C, which is the distance to the smallest outlier in terms of its nearest neighbor score. So now what's happening is, whenever I pick the 4th point from the database, I keep scanning the database again. And as soon as I find a nearest neighbor of that test point, which is less than C, I can immediately throw that point out, because it cannot be an outlier, because I've already found 3 outliers which are worse than this guy. On the other hand, if you find another point which is a more outlier than these 3 points, then you actually have to go through all of the points in the database. And only after that you can be sure that that is a more outlier point than the 3 you have already found. So what it means is, they have shown that if you randomize the data set well, on an average, this algorithm runs in linear time. The assumption being, for each point, you can find the nearest neighbor in constant time. But that doesn't really happen in practice. In most cases, what happens is, you have a cluster of points which are outliers, you spend a lot of time in that, and that is somewhere in between linear and quadratic. In most interesting cases, it's n raised to 1.3 or 4. That's what is the complexity. So the contribution from us is threefold. The first thing is, we are trying to speed up this existing technique, which is considered state-of-the-art, using an indexing scheme. While doing that, we want to make sure that the implementation is disk-based, because there are several ways you can speed this up. You can load the entire data in memory, and then you can do some efficient processing, and then say, I've found the outliers. But that's not the goal here, because the size of the data sets we are looking is roughly of the order of 10 to 100 terabytes, and you really cannot load anything close to that in memory. So the second contribution is, we have figured out that using our index, you can define an early termination criteria. By that, what I mean is, the algorithm can stop even before processing all of the data points. And this is interesting, because as you keep processing more and more points, there will be a stopping condition in which you can say, okay, I found all the outliers, I don't need to look at anything else. Doesn't matter what the size of the database is. The third is, we have developed a parallel algorithm which runs on multi-core machines, and also parallel frameworks, and that gives you better scalability just by splitting the data and doing some intelligent processing. So here is the first advantage of using the index. So note that a crucial part of the ORCA was how the threshold was determined. If the threshold increases very slowly, your cutoff, your prune rate will increase very slowly, because you cannot throw more and more inlier points out. So one of the interesting points is there a way of cleverly making sure that your cutoff increases very fast? So the intuition being, if you process the outliers first, you can make sure that your cutoff increases very, very fast. But the problem is, you don't know what the outliers are. So it's a chicken and egg problem. So if you don't know what the outliers are, how can you make sure that you process them first? So here is one solution to the problem. So we pick a random point from the data set. We call that the reference point. And we order all of the other points from this fixed point, with the highest distance from this reference point being the top. So here is the example. So the blue points are, let's say, my normal points, and the red points are the bunch of outliers that I have. If I pick a random point from the data set, more often than not, I'll pick one from the blue. I may pick from the red, but let's assume that I'm picking from the blue. And if I order the points, all the points in the database as distance to this green point, with the farthest being at the top, then the red will come first, then the blue, and then the green. So now note that this is just a one-dimensional projection of your point, based on a fixed distance to the reference point. And if I, instead of now processing the data set the way it's given to me, I will rather process it the way it's ordered according to this reference point. And by this, there is a better chance that I will process the red ones first, and that would increase the cutoff faster. So this is the experimental result. So these are 3 different data sets. The red curves are for the traditional algorithm, which is ORCA, which is roughly linear. And you see that how the cutoff increases. On the x-axis are the number of data points being processed, and y-axis is how the cutoff increases. And the blue one is our algorithm, which we are proposing, which is iORCA. So in almost all cases, iORCA has a far higher rate of cutoff increase than ORCA. In fact, in the last one, the data set, the reference point was chosen so brilliantly that at the first iteration, it got almost all of the outliers, and your cutoff is almost at the very top. So the advantage too for this indexing scheme is how do you find the k nearest neighbor faster? So on the one hand, you need the cutoff to increase fast, and on the other hand, you also need to find the KNN very, very fast, because that's the bottleneck of the computation. So it turns out that you can exploit spatial locality of the points using this index to find the KNN faster. And this happens this way. So when I want to test for a point or find the nearest neighbor of, let's say, the purple point, which is in the index, I don't know if you can see it, but it's number 1. So instead of processing, again, the points from top to bottom to find its nearest neighbor, I would rather do a spiral out approach. I'd go with top, bottom, top, bottom. And what that means, essentially, is I'm exploiting the spatial locality because these points are grouped together in that specific order according to a fixed distance. The assumption being, even in the higher dimensional space, you would hopefully have this ordering, but we don't know if it's guaranteed or not. So that's the other advantage of using this technique. And the third one, which I think is more interesting, is you can actually stop the computation after a fixed number of iterations, and that is dataset dependent. And the intuition is this. So let's say that we are given the index L, and the reference point, the green one, being R, and xt is any point which you are currently testing to find its nearest neighbors. So even before you do a disk access, because you have this index in memory, what you can do is simply find the distance between xt and r, which is the one on the right, and compute the distance between r and xn minus k plus 1. And n minus k plus 1 is nothing but the true kth nearest neighbor of this guy. So there are k points here. And if you add those two up and see if it's less than the cutoff, then xt cannot be an outlier. And this is very simple to verify. So here is the proof sketch. So why can we prune xt? Because xt minus xn minus k plus 1 is nothing but it's less than this quantity by triangle inequality. And since I know that xt minus r plus r minus xn minus k plus 1 is already less than the cutoff threshold, then the distance between xt and the true kth nearest neighbor of r will also be less than the cutoff threshold. And what it means is xn minus k plus 1 is a true kth nearest neighbor of r, which is less than the cutoff. Now, if you go down, in fact, so if you consider any point below it, those will also be less than c. And so you can prune xt out because it cannot be an outlier. So this is the first thing. The second thing is anything below xt, if you take xt plus I, that cannot be an outlier too, because of the exact same reason. So if you write this out, what you will end up with is this quantity. And this quantity by definition is always less than this quantity, because this quantity is bigger. So anything below xt can also not be an outlier. So that's the third advantage of this indexing scheme, and these three makes our algorithm run much faster. So once we have that, we were thinking if we can distribute this workload amongst a network of machines and still get the same performance, and how we design that algorithm. So this is what we called IDOR, which is outlier detection on ring, so distributed outlier detection on ring. And so the idea here is to leverage the distributed computing framework to speed up the distance-based outlier detection. So we are assuming that the machines are arranged in a ring for the sole purpose that there is a particular order in which you can send messages. So every node would do some computation in the network, they would send messages, and then that guy would refine that computation, and then it would send messages, and then this would keep happening unless and until the message comes back. So the first step is, of course, you split the data and send it to different nodes, and then the second part is each machine would build index on its own local data. So they would apply the IORCA framework, and you would start with a local threshold of Ci equals infinite minus infinity because you don't know anything about the data set. And there are two modes of operation of the algorithm. One is the push and the other is the pull. So here is the scenario. So these are the nodes, and we are assuming that the message goes in this order and comes back to this guy or this guy or this guy, depending on who initiated the computation. So in the push mode, you basically read a block of data from the memory for testing. You apply the IORCA technique to find its approximate nearest neighbors based on your just local data set. And if there are any points in the test set which are less than the cutoff, you simply throw that point out because it cannot be an outlier. But for the other points which you're not sure about whether, if they're greater than the threshold, you still cannot be sure whether they are truly less than the cutoff because somebody else might have your nearest neighbor. So that's the issue here. So what we do is we prune as much as we can in the local data set, and then we pass it to the next guy and let that guy prune it further. So in the push mode, that's what has happened. So you prune points with the KNN distance which are less than Ci, and the remaining points are sent to the next machine for evaluation. And that's so when the next machine gets the set of points sent by the first machine, what it simply does, it updates the k nearest neighbor of the test points. And by that, what can happen is you can throw some more points out because then some points can go below the threshold. But for some points, you still are not sure, so you have to pass it to the next guy. And this keeps happening in the ring. So if you started with, let's say, this size of the test block, when you keep going on the ring, your size of the test block will keep shrinking more and more. And the faster you can shrink it, the better it is because then you're doing some local processing and pruning it. And the idea is if all the points survived all the machines in the ring, if some points survived all the machines in the ring, then that point is a potential outlier and we have to do a further processing. And that's what is done by a master machine which sits on top of everything and does it. So here is the thing that the master machine does. So what it does, it updates the list of the current outliers. So it gets outliers from everyone which have survived the entire ring, and it updates the cutoff based on this list. So the cutoff is again set to the lowest from this list of T, and this broadcasts to all the machines for efficient pruning. So that's when the cutoff is updated, because in the next round your cutoff is evidently higher, and so you can prune more points. And the correctness is very simple because your cutoff increases monotonically. You can guarantee that you're not missing any outliers. So that's the basic proof. So in the experimental results, what we did was we tried on several data sets, and I'm showing only 4 of them. So the first one has 580,000 feature examples and 10 features. The Landsat has 275. So these are from the UCI repository. The MODIS is an art science data. It's very big. We just took 1 year's worth of data, which is 15 million points. The last one is what we are working on, the aviation data set. We again took 1 year's worth of data, which is 100 million points. But this one is extremely large. We took just a very small set. So if you look at the experimental results, so these are 4 different ones. On the x-axis, I have the data size, and y-axis, we have the running time. The black one, I'm not sure if you can see. Okay, the black one is the time required to build the index. That's the pre-processing of our algorithm. The blue one is the actual running time of our algorithm. That includes the black time. So it's the total time. And the red one is typically the time required for ORCA or any other disk-based algorithm to run. So in most cases, we see that there is a speed up of 5 to 15 to 17 times. So that's the typical speed up that we see by just using our technique without any parallel processing. Now, if you apply the parallel processing, it speeds up anywhere between 1.2 to 3.5 times on various number of machines, like 3 to 7. But to me, it seems that this is really under what we are expecting, and one of the reason being our implementation was done in probably in not the most efficient manner. We used MPI, which probably had a bigger overhead of the communication. And the other problem is that in the centralized scheme, there is a stopping condition by which the algorithm just stops and doesn't do anything. What was happening here is for the first few iterations, when both the algorithms performed equally, the distributed algorithm is a huge advantage because then you were distributing the workload. But for the later few iterations, the centralized algorithm was beating it because all it needed to do was just check that in-memory condition. And while this one was having an overhead of message passing, sending a termination criteria, and those things. So that probably was one of the reasons as to why the speed up was not that great. So in conclusion, for this work, we developed a sequential and parallel outlier detection method which significantly beats the other existing methods, and we have tried several other methods. Some uses clustering as a preprocessing step, some uses PCA as the preprocessing, but ours is much faster and very simple to implement. The algorithms are probably correct, and the way we thought about it is to always go for a disk-based implementation because of the sheer size of the dataset that we have. If you think about a clustering-based approach, they were all in memory because you do the clustering by loading the data in memory, which we avoided. And the third one is both the algorithms can terminate even before looking at all the test points, and that's a huge advantage considering the size of the dataset that we plan to apply this to. So this concludes one part of my talk. So the next part of my talk is about distributed model fitting and fidelity checking in large networks. So what I'm talking about here is, let's say that you...
Yeah. Can I ask a question about
sure.
the previous one? So how sensitive is it to the choice of reference point?
Oh, it's hugely sensitive. So if you choose a reference point, let's go back. So if you choose a reference point from one of the red ones, you would be back to Orca, essentially.
Yeah.
So it's not worse than Orca, but of course it's not as good as I'm showing here. So one of the ways you can do is you choose multiple reference points.
Okay.
And then take an intersection of your choice and then find the candidate set for each k-name. That really helps. We did some experiments on different data sets, and that really helps.
So the results here are
just one. No, it's
one and randomly picked.
Exactly, one and randomly picked.
Okay, because you could also kind of, as you collect the data, have a running average also.
Absolutely.
Then use that, and that would be probably the best.
Or maybe take the median or the mean of the data. So I think those are very good open questions that we are still trying to think and solve. Even I think maybe take a sample, do a PCA, and then the projection would also be even better. Yeah. So we are trying to do that, but some of the data sets are quite big in the number of features. So doing PCA is a challenge. Yeah. So we're trying to see if there is a sweet spot which is interesting. Yeah. Okay, the second part of the talk is about large-scale model fitting and monitoring that model in a dynamic environment. So imagine that you have a huge number of nodes in the network, and the data in those nodes is constantly changing. You have a prior knowledge of a model, let it be just a regression model, that's what I'm going to talk here. And how do you asynchronously track whether the model has changed or not without always gathering all the data? That's the focus of this work. This again was a joint work with my colleagues, and we presented this at SAM conference this year. So this is the same kind of roadmap: introduction, the problem definition, and what we are trying to solve here, then the algorithm, and some experimental results, and the conclusion. So this is the problem setup. So we are given an input data set which consists of two parts. The first is the set of inputs, x, and the second is the output, which is typically the target. And there is an underlying linear function which maps your input to the set of output. So it's a function from RD to R. For linear models, you assume that fx and y are well behaved and follows this linear criteria. And the goal for regression is simply to estimate these weights, or a0, a1, and so on. It's well known how to do that. If you just take an x transpose x inverse x transpose y, you can always do that. Here I'm not going to talk about the scenario where x transpose x is huge, so you can't invert it. But let's, for the time being, assume that you can invert it, and it gives you a good model. And so A is, you can always find A using this technique. So let's say that we know how A is, and we have found out A. Now we want to see how good is A. So there are several goodness of fit measures. One of them being what is known as the coefficient of determination, or typically known as R-square fit. So this is the definition of the R-square. It's 1 minus, the numerator is the sum squared error of the true versus the predicted, yi minus yij hat whole square, and the denominator is simply the variance of the actual value. So it's yj minus summation over yj by m whole square. So you can see that for perfect models, or models which are very well behaved, yj minus yj hat are equal, and so r square equals 1. On the other hand, if the model is very bad, your r square can actually be 0, and that happens when your average when you're always spitting out the average answer for whatever instance that you're seeing. So if your y hat is summation over 1 over m yj, then you will always get r squared to be 0. But what I'm saying here is r square can range from a value of minus infinity to plus 1. You can always have minus infinity because you can choose any arbitrary model and then you have no lower bound on r square value. But for the most practical cases, we will assume that it's between 0 and 1 because you can always say, I'll approximate the model with an average model. So what's new? So all this is known and very well studied in the statistics community. So what's new? So what we're trying to do is a little different. So we are saying that if you have a large number of nodes in the network, let it be a data center connected in a peer-to-peer or any other setup. It can even be any other routing technology. You have a data set at each node, which is x1 through xn. And x is also time varying. So x is the union of all data. Here I'm assuming that the data sets are disjoint and there is no overlap between them. And the goal for us is to compute regression models on x, not just on x1 through xn. So where can it be used? It can be used in real-time fault detection or health assessment in large-scale enterprise servers on the cloud. And we have some data where we are trying to apply this. The second one is smart grid applications. That's something we have experimented out here using our smart grid data from one of the open source data sets. The third one is you can actually track evolving topics in a text domain using sparse regression models. So I'm not going to talk about sparse models here, but it's very easy to see how you can apply the exact same technique for sparse learning. So here's the formal problem statement. So we are given a data set x1 through xn at each node. We're also given a threshold, which is between 0 and 1. And the threshold is the same at all nodes. We also know that there is a communication infrastructure between node pi and pj, and that is ordered in the sense that the first message should be delivered first and not later, because that alters your updating of the system. And we are also given a pre-computed set of weights at an earlier timestamp. And this is essential because I'm essentially talking about a monitoring scenario where you have done something and then you're trying to track whether it's still correct or not. And the goal for us is to maintain a regression model A at any given time such that the R square computed on the global data, not just the local data of the node, but the global data is greater than that epsilon that you have selected. So there are three solutions to this problem. The first is what is known as periodic algorithms. The second is incremental algorithms, and the third is reactive. So in the periodic algorithm, what happens is periodically you sample data from the network, you rebuild the model A and see if the last model and the new model is good enough using some statistical test of model fit. In the incremental algorithm, what you do is you have an old model, and whenever there is a change, you update the old model with the new model using some clever algorithm. The third is what we are suggesting is you track the model with respect to the data, and whenever there is an alarm that, okay, this model doesn't fit it, then we resample data from the network, build the model, and then keep checking again. So that's kind of the two-phase reactive closed loop kind of a solution that we are proposing. Of course, the periodic algorithm wastes a lot of resources. The incremental algorithms, as we know, are extremely efficient, but it's very difficult to develop them, and that has to be hand-tailored for each of the problems that you're trying to solve. The reactive algorithms are very general, so there are solutions for almost all of the data mining problems that we know of. They're very simple to develop, but they're very, very efficient in terms of the communication complexity. So here is the details of the work. So what we are saying is, let's for the time being assume that each node has a vector vi. The exact definition of the vector I didn't present it here because it's a little complicated to write it in terms of the local data set, which is yi and yi hat, which is the true value and the predicted value. And based on that vi, we want to do the model checking. And we also define a parabola g, and the way it's defined as it's b1 minus 1 minus epsilon b2 square, and this epsilon is the user defined epsilon given to the system. So here is the details. So remember the R square formula that I presented earlier. It's basically the sum squared error divided by the variance. And what I've done here is, instead of writing it as a single sum, I've just written it as two sums. So first, the inner sum is you do it over all nodes, first nodes, any nodes data, and that is summation over j equals 1 to mi. Mi is the number of data points at node I, and then you sum over all nodes. So instead of having one sum, we have two sums now, and the denominator is also the same. So instead of having one sum, you have two sums. So the R square that you got earlier is the same as the R square that you should get now. It turns out that if you want to check whether R square greater than epsilon is the same thing in a geometric setting, checking whether the convex combination of these vectors vi, which is the local vector at a node, it lies inside the parabola. So what it means is if you gather all of these vi's, take a convex combination and weigh it by the number of points that this pair holds, take the sum over all of them, get this vector vg, and see whether it's inside the parabola. That's the same thing as doing checking whether R square is greater than epsilon. Still, it's inefficient to compute Vg at each time step, because what I've proposed here is what you can do is at every time step you can compute these Vi's, you can gather them, you can do this sum and see whether it's inside the parabola, but that's no different than gathering the whole data essentially. So here is the geometric interpretation. What it's saying is, so this is the contour of the parabola, and if Vi is inside the parabola for all of the pairs, then Vg will be inside too, because it's just a convex combination, and convex combination will always lie in the convex region. But this is not true for any point outside the parabola, because the outside of the parabola is by definition not convex. So what you can do is you can draw half spaces, you can approximate the parabola using some of these half spaces which are here, and then you can apply the exact same thing. So if all of the Vi's lie in a particular half space, then Vg will also lie in the same half space. So that's the geometric interpretation of the problem. Now the question is, how do we check this global condition more efficiently without gathering all of the peers data or the machine's data at every single time step? And for that we need some local statistics vectors. So these are just mathematical definitions, but the intuition is you have a knowledge which is essentially your local data, which is Vi, plus all of the information that you have gotten from your nodes, your neighbors. It's only the neighbors that we are considering. So SJI is all the information that I has received from J. Agreement is whatever they have shared, withheld is whatever they have not shared. So this is the difference, and a message is typically whatever you have and whatever you have received. The difference of that two, just to prevent double counting of the same message. So note that this is a cyclical definition, because you have SJI here and then everything is defined with respect to everyone else. But when the algorithm starts, your SJI is 0, so your knowledge is set to Vi. Agreement is 0 because you have not sent or received anything, so it's 0. And your withheld is essentially your Ki, because you have not sent anything, so everything is withheld. And similarly, your message is equal to the knowledge, because that's what you're going to send the first time. But as the algorithm progresses, what happens is you start collecting more and more information on SJI, and your knowledge will start to differ from your Vi. And that's when the interesting stuff would start happening. So what we essentially want to show is, if I apply the parabola condition to this Ki and figure out if just by looking at G of Ki greater than 0, or in other words, if this one lies inside the parabola, if I can guarantee that that means that the global vector is also inside the parabola for all the pairs, that's a very interesting point. Because then you don't need to gather all the data. You essentially have gotten rid of this summation here. And that's what is given by this global condition. So what it says is, if all of these three vectors or the sufficient statistics are inside any of the convex region, and that convex region can be inside the parabola or in any of the half spaces or any other convex region, then it's guaranteed that the Vg, which is the global vector, is also in the convex region. And it's pretty easy to show this, because all you do is you pick any two random pairs and then you let them exchange all of their data, and you can mathematically show that just by applying the convex rule, it always remains in the convex region. So you can now define this global condition and detect it based only on the local conditions. That's what we are trying to do. Back to the convex region, it's nothing different. So inside of the parabola is G A equals G of A greater than 0. That is convex by definition, so there's no problem in applying the rule. On the outside, you have to draw these tangent lines because you don't have the good convexity part of it. And so that's how we approximate the outside of the parabola to apply the theorem. So what the local criteria allows you to do is, it allows a node to terminate and stop sending messages whenever its local condition holds. Doesn't matter whether it has received a message, whether its local data has changed, a new node has joined, a node has dropped, or anything. So that's all the node needs to guarantee. And it will still guarantee you eventual correctness. By eventual correctness, what we mean is when the computation terminates, you'll get the exact same answer if you had gathered all of the data and found the R-square. So that's the beauty of it. It's quite good in pruning messages. I'll show you in the experimental section. And allows the node to sit idle and not do anything unless there is an event. And an event are 3 scenarios: sending or receiving a message, a change in its local data, or a change in the neighborhood. So unless one of these happens, you don't need to do anything. So here, this is a flowchart. There is nothing in there basically. So what it's saying is, so you take a local data set and an error threshold epsilon, and you want to basically monitor whether R-square is greater than or less than epsilon. So you initialize your VI, which I have not shown here for simplicity, compute the sufficiency risks, the knowledge, and all those things. You define the convex regions, and those convex regions are uniformly defined across all of the machines in the network, and then you keep applying this convex rule. So you start, you do the initialization, you apply the convex rule. If it's satisfied, you don't do anything else. You go back and send messages and then wait for events to happen. That's essentially what you're doing. So up till now, what I have said is how you track the model if it has changed. The next part is essentially building on top of that. So let's say that we have detected that there is a change. How do we recompute the model and update the model? So the solution that we have is a very simple one. It's based on the converged cast tree. So every peer or every node in the network would simply send its data or a sample of the data up the tree, and then when you get all of the information at the node, you rebuild the regression model, and then you percolate it down the tree. And for that, what you need are two quantities, x transpose x and x transpose y. And note that x transpose x is nothing but a summation over all of the local peers. So each of the local peers can compute x transpose xi, x transpose xi, and they can compute them here, and then they can send it up the tree, and the next peer can simply sum it over all of its children and then pass it up. And that's how you can essentially compute the true A, because it's nothing but a summation over these quantities. So here is the experimental setup. So we did an experiment. So you had a question? Oh, sorry. So here is the experimental setup. So we did a dynamic experiment where we were changing the data at different levels. So this is the timing diagram. On the x-axis, you have time. So what we did was every 20,000 simulated ticks, we changed a fixed percentage of the data of the nodes. So I think we changed 20% of the data at each node, and we assume that each node has a fixed length data buffer. So you return some old data and put it to some fresh data. On top of that, at every 500,000 clock ticks, which is a bigger time period, we change the distribution from which the data is sampled. And here distribution simply means changing the coefficients of your linear model. So here is the data description and how the peers react to the change. So this is the data. On the x-axis you have time, and on the y-axis you have the actual value of R-square as seen by all of the peers. So this is an overlay over all peers data. So if you look at the odd epochs, what happens is the R-square, the average R-square value is quite high. It's close to 0.7. And the reason being, we give each pair a similar set of coefficients from which we were also generating the data. So those two coefficients were similar. And that's why there is a higher model fidelity with respect to this R-square value. On the other hand, for all of the odd epochs, we change the coefficients of the data generator while keeping the coefficients of peers the same. And what it means is there is a very low fidelity of the model. So that's what is happening.
So the peers don't re-estimate the model?
So this is only for detection purposes. Okay. So I am not allowing it to recompute the model. That's the next experiment I'll show. And the red one is our epsilon chosen, which is 0.5, such that there is an exact half. The probability of true positives and negatives are exactly the same. And this is how the peers behave on the accuracy side. And the x-axis is time, and on the y-axis is accuracy. So between 0 and 0.5, which is this region, you see almost 100% fit. Everybody is saying that the model is correct. Then whenever the data changes, that's when they start communicating, and this is reflected here too. That's the time versus messages per node, and then there's a huge drop in the accuracy because that's when they're unsure about what's happening. They need to gather some more evidence, and then you again see a jump in the accuracy. That's when they say, okay, everybody's outside. Everybody is saying that the model doesn't fit the data. Here they are saying the model fits the data. And if you look at the messages, that's interesting too. Whenever there is a change in the distribution, you have a sharp jump in the messages. But on these instances, there's a very little change in the very little number of messages going on. But this is still dynamic. So it's not that I'm changing the data here and here. Throughout, I'm changing the data. But because it's the model fitting criteria, it's the algorithm is doing what it's supposed to do efficiently. So one of the advantages of using this kind of algorithm is what is known as local behavior. What it means is these rules, the rule that I talked about is very data dependent. And whenever the data changes, there is something action going on. So you really can't characterize it by writing some equations when the data will change or what kind of analytical results you'll have. So what we did was we incremented, we changed the network size from 500 nodes to 4,000 nodes, and we plotted the accuracy of the peers and the number of messages it say. So what's happening is, as the number of nodes increases, the accuracy remains almost a constant, which is the left one, and the messages per peer is also a constant, which means that you can infinitely increase the number of nodes in the network, and the scalability will not be hampered. And the reason it's happening is these computations are very local to a peer. So if you change the data at each peer, it propagates to a very few number of nodes in the neighborhood before it subsides. And that's what is being reflected in these experiments. And this is true for other local algorithms as well. So this is the second part of the experiment where I'm essentially closing the loop and allowing the peers to recompute the model. So I'm starting off with a very bad estimate of the model at each peer, a random guess. So you have a very bad value of R-square. The peers see that this is indeed the case, so they recompute the model, and for the latter half, when the data is in line with the model, you see a very high value of R-square. Then again, I'm randomly changing the data distribution model to a different one, and there's a drop in the R-square, and this keeps happening. And that's what reflected in the monitoring messages. And this is the number of times computation happens. This is a cumulative graph. So every time the data changes, there is a number of messages which is being passed to collect the data and rebuild the model. And that's what I'm showing here. The last experiment was an application of this algorithm to a smart grid operation. So what we were trying to do is predict how much of CO2 would be, carbon dioxide would be used, carbon dioxide would be released based on two factors. One is how much of wind energy is being generated and what's the energy demand. The assumption being higher CO2 means less fossil fuel, more fossil fuel is burned and less renewable energy is used. So we collected about 9 months of data from one of the grid operators in Ireland, and January through September, and each month of data we assumed it to be one epoch. We built a model based on the data between January and February, and we were trying to see if the algorithm would detect, because there is a huge demand, there was a drop in the carbon dioxide release between May and June. That's what is known. So the idea was, can the algorithm detect that change? So we built the model from this period, and then we piped the data in and kept changing the data for each month. And the algorithm did actually pick this up and said that the model doesn't fit the data. So this again is in the open loop mode, where I'm not allowing the peers to rebuild the model, just using as a detector. And if you look at the messages, that's also is reflected there. So in conclusion, so this is the first work, as we know, in monitoring R-square on really large distributed systems which are asynchronous in nature. The algorithm is, of course, provably correct. It's highly efficient and converges to the correct result. And R-square is scale-free in the sense that it lies between 0 and 1. So you can pick a number, and that's it. Unlike many of the other works on thresholding, where you have to know what epsilon is. That's very dataset dependent. even some of my earlier work was that. In short, I want to acknowledge the NASA System-Wide Assurance Technologies project. This is under the Aviation Safety Program, of which I'm a part of. And for many of the papers and some of the open source codes, this is where you can download them. I think that's pretty much what I had.
I have a question. So it seems like there are kind of two fundamental modes. One where the distribution drifts naturally and you want to adapt. Another one is where you have a critical event happen.
Yes.
Things go out of whack, you get the alarm, but you don't want to screw up the model. You want the model to remain.
Exactly.
I mean, do you think this is just something you have to pre-decide earlier, or can you have some sort of natural mix of the two to where the model would know whether to adjust, or just to kind of season the fire alarm and then go back to the previous learned state?
So the way the algorithm works, you can basically set it at the time in which you want, the type of detection you want to do, essentially. Okay. That's not something you have to decide before the algorithm starts. So the algorithm would still decide, okay, this is the alarm for which I'll rebuild the model, this is the kind of alarm for which I won't be rebuilding the model. I think that kind of thing would be very important.
It would be like a second layer of inference.
Exactly, right. And depending on some hypothesis tests and what kind of, what's the significance of the alarm, essentially. This is a very simple model where I'm just saying, okay, it's out. Rebuild the model. Yeah.
Questions? Because I just too much.
Yeah.
All right, let's thank you.
Okay, thank you.